Indoor scenes have many articulated objects with which we interact in our daily lives. Therefore, a holistic 3D understanding of the world requires modeling how people interact with articulated objects. While there has been progress in dynamic 3D reconstruction of humans, animals, and rigid objects, there is much less work on human object interaction with articulated objects. In this paper, we canonicalize the task of RGB video to articulated 3D human object interaction reconstruction to carry out a benchmark of recent methods that can be used for this task. We define the task as given an input single view RGB video of a human interacting with an object, reconstruct an articulated model of the manipulated object including static parts in green and articulated moving parts in blue. We decompose the evaluation into three different aspects, including reconstruction, that is, the shape of the reconstructed object should match the object in the video, pose, that is, the inferred 3D pose of the object should match the input video, and motion, that is, the moving part of the object should have accurate articulation parameters including axis of rotation and degrees of rotation. The task is challenging because it is hard to acquire ground truth 3D data for direct supervision. Humans interact with a range of diverse articulated objects. The human and objects are both moving and changing in appearance throughout the video, and there are often significant occlusions between human and object due to a fixed viewpoint of the video. We systematically benchmark five families of methods including 3D plane estimation or 3D ADN, where the moving parts of the objects are estimated using a 3D plane, 3D cuboid abstraction or cube OPT, where the articulated object is approximated using oriented cuboids, CAD model fitting or D3D HOI, where a CAD model is retrieved and positioned to represent the object, implicit fields for articulated objects or ditto, where an implicit neural representation based model jointly predicts part level geometry and articulation between parts. Free-form mesh fitting or laser, where an arbitrary polygonal mesh is constructed for the observed object. Our evaluation metrics are designed to measure the three aspects of reconstruction, pose, and motion as we mentioned earlier. For reconstruction, we first compute ICB between the ground truth and predicted mesh to align the meshes. This helps us to disentangle reconstruction from pose evaluation. We then sample points on both the predicted and the ground truth meshes. We then compute the chamfer distance between the sampled surface points on the ground truth and predicted articulated object mesh. For pose evaluation, we measure the rotation and translation error based on the prediction to ground truth mesh alignment transformation matrix calculated by the ICP. For the scale error, we measure the discrepancy of the ratio between the maximum dimension of the ground truth and predicted mesh. Lastly, for motion, we compute the Euclidean distance between the motion origins, angle difference between the motion axis, with and without taking direction into account. For the state error, we use the absolute difference between the predicted and ground truth articulation angles. Here, we show example results using all five methods. Despite having privileged ground truth information, all the methods make significant errors. In the second column on the top row, CubeOPT gets the motion axis wrong, and D3D-HOI in the top right also struggles with inferring a correct pose for the object and the moving part, with the trash bin lid opening from the side instead of the front. We also note that laser and 3D ADN struggle to predict the correct pose of the articulated object. Now, we show some quantitative results. We threshold the errors to get accuracies for each of the metrics to make it easier to understand. As we can see, D3D-HOI with ground truth CAD model performs the best on reconstruction metrics. For a fairer comparison, we also consider fetching a random CAD model over all models versus using one with the ground truth category. D3D-HOI RAND-CAD is comparable to CubeOPT, better on some metrics, while worse on others. Note that 3D ADN and laser struggle here as 3D ADN is unable to predict the base part, while laser cannot predict the moving parts of the object. Similarly, we note that having a fixed set of CAD models also helps the pose accuracy. However, Ditto outperforms all other baselines as it has access to ground truth point clouds of the objects. While D3D HOI with ground truth CAD continues to perform very well on motion accuracies as well, we note that despite being very simple, Cube OPT performs relatively well on motion estimation. Overall, we see that all the methods struggle to achieve decent performance on the task. D3D HOI with ground truth CAD models also achieve lower than 30% on combined accuracy of reconstruction, pose, and motion. Please refer to the paper for more details on the quantitative evaluations carried out in our benchmark.